Okay, good evening, everyone. Today we'll be talking about oxidation and reduction for chemistry. So over here, there is actually a few ways in which we can actually identify processes of oxidation and reduction, either through the oxygen, either is it a gain or loss of oxygen. Second would be by hydrogen, gain or loss again. Third would be the electron, whether the reactants have actually gained or lost electrons. And all these can actually be computed through the chemical equation, and that's where we will introduce changes in oxidation state. Then following this, we will identify redox reaction, where there are reactions that have both oxidation and reduction occurring at the same time. And lastly, we look at the agents that actually helps to catalyze some of these reactions. So first of all, what is oxidation? Oxidation, there's four different scenarios that can result in the substance being oxidized, or for us to actually know whether something has been oxidized. Number one is a gain in oxygen, meaning, right, let's say you have a reactant A. After the chemical reaction, right, this A will eventually gain some form of oxygen molecule or atom in that sense. On the other hand, for the hydrogen one, right, it's where this hydrogen atom is attached onto the reactant that you have, and after the reaction, this has actually been separated and lost, okay, in the form of either H plus or H2, etc. Then, of course, you have loss in electron, where initially you have A, and after the reaction, you have, in a way, lost some form of electron away from you. Now, one very common misconception is that this plus would signify the gain, which is not the case. We always look at the direction of where the arrow is moving to signify how the electron has been lost from the A. Then, of course, oxidation state will be the overall, in your ionic equation, you have on the top right hand superscript, you actually see a charge. That charge will actually follow the reactant, and from there we can see if there is an increase in the oxidation state, that means an increase in that numerical value. Then it has actually undergone oxidation. If it has reduced, it has undergone reduction. So one very common way to remember is by the acronym OIRIC. And this OIRIC, right, is where O represent oxidation, then I is then loss. So this will only highlight for the electrons as well as the hydrogens. You cannot use this particular acronym for other for the reaction or scenario for electron hydrogen, because only during oxidation is loss in electron or loss in hydrogen, whereas reduction, which is the R, is actually gain in hydrogen or it's gain in electrons. Okay, so just only these two particular scenario. So when a reduction is basically the opposite or the reverse of oxidation, where if oxidation gains oxygen, you will actually tend to lose. So this is like just now what we actually discussed. So so these are some examples in which we can actually look from the equation. Over here, we could see that we have an atom here, calcium, and they interact with another molecule, oxygen. Now, this plus indicates that this calcium and oxygen hasn't combined into one molecule yet. So they are separate molecules, in which calcium is a separate atom. In this case, right, only after the reaction, which is signified by the arrow sign, we could see that the calcium has actually gained the oxygen atom, and in this case we would say that calcium has been oxidized to calcium oxide. Now, do take note of the phrasing, how we actually form our sentence. We always start with the reactant, then after that we will say forming the product. And in this process, right, what actually occurred? How does it come about being oxidized? We talk about the scenario. Just now we saw four scenario. Okay, so four scenario in terms of either gaining oxygen, losing hydrogen, lose electron, and increase oxidation state. So we will always phrase our answer in this way, and we tend to conclude that is it oxidized or reduced. So we could see in this case for sulfur, this sulfur has actually gained in oxygen again, the oxygen over here. And so we would say that sulfur, which is a reactant, has gained oxygen to form sulfur dioxide, which is the end product. And of course, this will actually lead to sulfur being oxidized. Reduction will be the opposite, where we will start with, let's say, copper oxide. So in this case, we have this copper oxide, which is the reactant. Okay, you can see that all these are the reactant, followed by the product. The product will be the copper here. So it is very visible that we have actually lost the oxygen from copper oxide to form copper. And so the scenario will come in terms of why is it, what has actually happened, and therefore it has been reduced. So in our answer, we always follow this sequence. Okay. So what exactly then redox reaction? So this is a definition. Usually it comes out in exam if you are required to explain or to in the question they can come in from the point of explain why this reaction is considered a redox reaction. So basically, for something to be considered a redox reaction, oxidation and reduction must occur together. So a redox reaction is where a chemical reaction involving both oxidation of the substance and the reduction of another substance do occur. Okay, so for example, we can take a look at the oxidation for magnesium. So if we take a look at the one in yellow, so this indicates the change where magnesium actually gains the oxygen to form magnesium oxide. So this is a redox reaction. This is an oxidation reaction. And of course, reduction occurs at the other side, where water lost oxygen atom to form hydrogen. So this is a reduction, and together as a collective whole, this is what we call a redox reaction. This is another example where we could see the iron trioxide forming iron through reduction, and you actually see this equation quite familiar again in the chapter of metal after this chapter, because this is one of the key equations that you have to remember for extraction of iron. So next is of course your carbon monoxide undergoing oxidation to form carbon dioxide. So next we look at in terms of hydrogen. So for oxidation, for oxidation, right, it's whereby we lose the hydrogen. So same thing here, we would see that for the iron, for the H2S, they would actually lose the one hydrogen, or in this case, to lose two of the hydrogen to form your sulfur. So this would have actually indicate that it has lost. Sometimes you can also write lost how many hydrogen atoms. So in this case, you have lost two hydrogen atoms to form sulfur. Okay. Of course, ammonia, you can also come in here. Now, some students ask, must I lose all my hydrogen? The answer is no. As long as you lose at least one hydrogen atom in this kind of scenario, then you would have be considered to have undergone oxidation. So, for example, another one is, let's say we gain. So over here, we could see that the chlorine has actually gained one hydrogen atom, right, to form hydrogen chloride. And in this case, this is a reduced reduction. So which substance has gained hydrogen and what has it been reduced to? So we could see that over at this number 2, right, the nitrogen here has actually gained one hydrogen to form ammonia. And this is in the sense when it has gained the hydrogen, it has been reduced. Okay, we tend not to compare the hydrogen atom alone only. So so that's one consideration. Next is coming to electron. So for electron wise, right? Let's say we look at magnesium, a neutral magnesium atom. It is in group 2, so generally because it's in group 2, it will actually lose 2 electrons to form Mg2+. Now, one key thing to take note is this charge and the overall charge here has to be the same as the charge that is provided. So in this case, the charge of magnesium is plus 2. 2 electrons, so it's minus 1 times 2. So it's minus 2. So together, when the plus 2 and minus 2 comes together, it is actually 0. So that's where it represents the neutral charge. We tend to do the calculation based on the side of the equation. So this represents the right side of the equation. So the right side of the equation must be similar to the left side of the equation over here in terms of charge. Okay. Again, the phrasing comes in hand. We always talk about the reactants. Then later on, we talk about the product. And in between is what actually happened. Over here, we also do specify how many electrons are lost. So, and another thing to take note is we do write the charge. So usually to represent something like this is called the ionic equation, something that we have learned previously. For the other one is these are, if there's no charge above, these are normal chemical reactions. Again, you have to balance the charge of the electrons with respect to the overall charge of the whole equation. Okay, so for iron 2 plus, it will be actually losing 1 electron. So when you lose 1 electron, you could see that this 3 plus minus 1, you'll get a 2 plus over here. So that's where you could also indicate the overall charge has to be balanced. Okay, then of course, in this scenario is copper 2 plus gaining 2 electron, because this, when you say plus 2, you actually being as this 2 plus 2 electron has been absorbed into the copper 2 plus, forming a Cu. So that's why this copper 2 plus has been reduced to copper. We always start from reactant to product. We don't start from product to reactant in this kind of phrasing lah. Because if we always look at it from a product to reactant point of view, we don't follow the arrow direction, we will always be very confused. Is it reduce or oxidize? So in your secondary school curriculum, most of the equation are directional or single direction. There's only one exception, which is the formation of ammonia, which is a dual one. If not, it's your weak acids. So these are generally the ones. The others are usually single direction. So in this case, how many electrons has Fe3 plus gained? In this case, it has actually gained 1 electron. Okay, so the answer here is 1 electron. So again, things can start to be very complicated where you have too many reactions. But one rule of thumb is we always follow the reactant. So let's say this is the reactant of interest, copper. We will assume indirectly to what is the product that we want to actually form. So in this case, it will be copper to copper nitrate. Now, another thing to take note is in your chapter of ionic equation, we also do see how we can actually form ions. So your CuNO3, right, you can actually separate it out to a Cu2 plus and 2 NO3 minus. Of course, in this case, it helps to break down further where the copper from Cu to Cu2 plus, you could see that it has actually lost 2 electrons in order to form this particular reaction. So the reason why I never add the 2 electrons here yet is because over here the charges still balance, but if I were to write half equations, it will look something like this. Okay, so this is something that we will also slowly see. Then of course we have silver. Now things that can be ionized, right, are usually your ionic compound. So one way to look at it is your aqueous. Anything that is of the solid, liquid or gas state, they tend not to form ions that easily lah. So they usually make it the same. So in this case, we would see it to be Ag plus and of course 2NO3 minus. And of course, when we write the ionic equation, we realize that this NO3 minus can actually be cancelled from each other, leaving this particular ionic equation. So we usually can represent it to explain in, we have to do one more step if we want to explain oxidation and reduction if let's say we are using from a chemical equation point of view. Because writing the ionic equation helps to really see the electron movement in terms of the charge better. Next is oxidation state. So what exactly is an oxidation state? It is the charge of an atom of an element that would have if it exists as an ion in a compound. So what happens is later on we will see how to go about calculating this oxidation state. This oxidation state, in other words, right, is actually very similar to the overall charge of the atom within that ion. Okay. So when we look at it, the overall charge for all these is actually neutral, so it has an oxidation state of 0. However, as we can see, some of them are already able to follow as an ion. Therefore, the oxidation state of a simple ion is actually exactly the same as the overall charge. So let's say sodium Na plus, right, will be +1, Mg2 plus is +2, etc. Now, this is also very similar to where from this oxidation state, we can also guess what is the group that this belongs to. Like sodium is in group 1 because it has an oxidation state of +1. So more often than not, when we actually do a periodic table, the group 1, group 2, group 3, 4, 5, 6, 7, and group 0. So the oxidation state, right, or the charge will still be about the same, where group 0 is 0, it's a -1, -2, -3. Group 4, it can be +4 or -4. It really depends on the situation. Then, of course, you have a +3, +2, +1. Now, transition metals, right, generally, some of them actually have more than one oxidation state, meaning, right, they can have two kinds of numerical value. For example, copper got copper 1, so it's Cu plus, so it's +1, or copper 2 plus, or copper 2, which is copper 2 plus, which is +2. You also have your iron 2, which is +2, and of course your iron 3, which is +3. So generally, these are the more common ones that you have to be familiar and remember. And of course, to determine some oxidation state, there are generally some rules. So group 1 tends to have an oxidation state of +1 in the compound, meaning group 1 of the element. Okay, so in this case, all like the sodium would be Na plus, your potassium is also 1, so all these will actually have a +1 oxidation state. But this is different from the other non-metals. So when we look at oxygen, right, it will be -2. Um, Chloride will be -1, -2, -1. And this one follows according to the group number or naming the charge. So some of these elements will have a fixed oxidation state. So even like in group 2, you can also have a +2. Some elements having the fixed oxidation state in their compound. So like for example, in this case, all the hydrogen here, right, regardless of where it's combined, it's always H plus or +1. Then, of course, some elements would also have a fixed oxidation state in their compounds, like oxygen. In this case, it will be the anion, so it's a -2. Um, and of course, the oxidation state of all atoms or ions in a compound usually have to add up to 0, which will indicate no charge here. And this would, and please don't write a 0 up there. Basically, these are all your neutral or stabilized compounds. So the sum of all the individual oxidation state for your atoms, so it's like magnesium is +2, chloride is -1. When you add them up, it should be 0. Why do we have 0 here? Because there is 2 chloride atoms, so we actually have to multiply by 2 to the -1. Okay, and then you'll get 0. So this +2 belongs to magnesium, whereas the whereas the 2 multiplied by -1 belongs to the chloride ion. Okay, and because there's 2, so you have to multiply by 2. So this will actually allow us to identify the individual oxidation state. Now, one very key thing is for calcium, right, we usually separate it by the capital letter. So in this case, there's 3, which is calcium, carbon, and oxygen. So how then are we able to identify the oxidation state of carbon. It's not from the periodic table, whereas we have to actually calculate it. So first of all, if carbon is the one of interest, so this is the one we have to calculate. The others we can refer by the periodic table, which is PT lah. And the overall is 0. So what can happen is calcium has an oxidation state of 2 because from group plus 2 because it's from group 2, and then oxygen is group 6, so it's minus 2. So in this case, you have calcium, which is plus 2. And let's call carbon oxidation state as X. Okay, so when it plus X, because there's only one carbon, plus 3. Why 3? Because 3 oxygen atoms. Then each of the oxygen atoms, the charge is minus 2. In total, this will be equal to 0. So we have, when you simplify it, you have 2 plus X minus 6 equals 0. X minus 4 equals 0. When you bring over the minus 4, it will be converted. So this is basic your maths. And therefore, we could see that the charge, the oxidation number of carbon is actually plus 4. Of course, if there is more than 2 carbon, then you will divide accordingly, but in this case, it's like this. Another thing to take note is we do not consider the coefficient, the overall coefficient of the whole molecule as part of the multiplication. We only calculate based on the individual molecule, one individual molecule within the reaction. So sometimes we can also calculate the whole item. In this case, like let's say sulfur the sulfate ion, right, is SO42 minus. We want to identify what is the oxidation number of sulfur. So what we want to do is we can let it be X. So X plus 4 molecule of minus 2, which is oxygen. And the overall charge, because it's 2 minus, right, it becomes minus 2 rather than 0. So if we simplify it, we do our math. Okay, the oxidation state or number of sulfur is actually plus 6. So from this you can actually see that it doesn't necessarily have to follow the periodic table one. Usually this is something that we want to consider and calculate. And it's a question that's quite common, especially in exam where we have to calculate the oxidation state to gain the mark. So oxidation usually occurs when the oxidation state increases, meaning initially it's 0. You repeat the steps and you realize it's 0. This one is very straightforward, you can see already, or plus 2. So we could see that after the reactant to the product, right, you actually gain in the oxidation state of plus 2. So how we phrase our answer is, the oxidation state of zinc, which is the reactant, has increased from the oxidation state, which is 0, to plus 2 in the product. So again, it's the structure is always reactant, the process, the product, and finally you have to give a conclusion. Is it oxidized or is it reduced? Okay, so visibly, sometimes we can actually, because in chemistry, sometimes we couldn't really see the molecules, how it interact, but we can see color. And the color will help to indicate whether is there a reaction, and based on the reaction, we can actually tell is it oxidation or reduction by figuring out the chemical equation. So oxidation actually occurs when the oxidation state of a substance increased, and generally these are some of the things when we compare, we always compare similar atoms of the reactant with the similar atoms of the product. You cannot compare, let's say, you cannot compare chlorine with Br2 here. They don't share any common atom, they don't share any common electron. So comparing this will not gain anywhere. You must always compare, let's say, okay, I see a chlorine, so I'm going to compare with a chlorine. Or if I have a bromide, I'll compare with a bromide. So we can see from bromide to bromide, it's minus 1 to 0, so you have actually undergone an increase in oxidation state. So you will oxidize. Whereas for chloride, the chlorine, right, is actually from Cl2 which is 0 to minus 1, and in this case it has reduced, it has decreased in oxidation state, therefore it has undergone reduction. So reduction occurs when the oxidation state of a substance actually decreases, And this oxidation state of the chlorine has decreased from 0 to -1. Okay, how are we able to identify redox reaction? The fastest way and the safest way to get anything is by the equation, calculate the oxidation state. If you look at based on oxygen, hydrogen, or electron, it may confuse you further. It may be some of the reactions may not even have all these, so you can't really tell. So try to train yourself use with oxidation state, and then it will be more clearer lah. So in this case, we could see that zinc has gained in oxygen to form zinc oxide, and this is oxidation. Whereas copper oxide is reduced to copper by losing the oxygen, therefore it's reduced. So together in totality, because you have undergone both oxidation and reduction in the same equation, therefore it's a redox reaction. Okay, this is another example, but in terms of electrons. Then we have one based on oxidation state. This is the one that I usually promote students to actually do and to explain, because number one, some of these questions, they would also ask you to calculate the oxidation state, and based on the oxidation state, you will then be required to be able to maneuver some of these items. Okay, all reactions redox reaction? Not really. Actually, the answer is no, because neutralization and precipitation reactions are examples of non-redox reaction, meaning you won't have oxidation and reduction occurring within the same reaction. So one very good example is over here, your hydrochloric acid reacting with the base sodium hydroxide to form sodium chloride and water. We could see that there is no change in oxidation states of the hydrogen and oxygen. So neutralization reactions are not redox reaction. Do remember this sentence, as this might be one statement that can be asked during exam. Precipitation is another one. There is no change in oxidation state, and therefore precipitation reactions are also not redox reaction. Finally, we look at the agents. So what is so special about these agents? So these agents are add in to help to promote a particular reaction, like to get it oxidized or to get it reduced. So if let's say you use an oxidizing agent, you want to cause another substance to be oxidized. So how you can go about doing it is either you give your oxygen, or you remove hydrogen, or you accept electrons. And at the end of the day, it itself will get reduced. Okay, so this is the main thing to take note of. Its role is not to oxidize itself. Its role as an agent is to oxidize another chemical formula. And in this process of oxidizing another chemical formula, itself gets reduced. Likewise, if we talk about reducing agent, it's the opposite, where itself gets reduced. Itself it gets oxidized, but it reduces another substance. And how it does it is either by reducing oxygen, removing the oxygen, giving the hydrogen, or donating the electron. So for reducing agent, we would expect that reducing agent to actually reduce in oxidation state. Because we would expect that reducing agent to actually gain in oxidation state because it has been oxidized. So these are the list of common oxidizing agent and common reducing agent. One of the more common one is this one, your potassium manganate as well as your dichromate. Why? Because the color is very distinct. So potassium manganate is tend to be purple color when it has already undergone when it has already oxidized something else. You will see that there's a change in the color. It becomes either colorless. The other common one is your potassium iodide, which is another color. It's like more or less like yellowish kind of color, which you will see later on. So what we can see is through this, when something is being oxidized, we could say that it's actually more or less a reducing agent. And when itself gets reduced, we could say that it's an oxidizing agent. When it gets oxidized, we could say that it's a reducing agent. So same thing again, quite straightforward. Now, how do we test for oxidizing agent? So when we test for oxidizing agent, we have to we want to see whether it will get reduced, right? So one thing we want to see whether the oxidizing agent gets reduced, we will actually put in a reducing agent. And this reducing agent is actually a potassium iodide. So what will happen is potassium iodide tends to be like colorless. So when it has undergone reduction, when the potassium iodide has undergone oxidation, okay, by the oxidizing agent, it will actually form a brown solution. On the other hand, the opposite is true for oxidizing agent, where for oxidizing agent, right, if let's say we are going to want to see if the substance it contains oxidizing agent, we will actually have a few ways to go about doing it. Just now we talked about the potassium iodide. Now we talk about a starch iodide paper. Okay, so this one we will see that there is actually a change in color. Though this is not really highly tested, this method for test 2, we tend to use test 1 more often. Okay, then of course the other one is, let's say you want to test for reducing agent, right? We will then throw in an oxidizing agent, and of course potassium manganate is one such thing, where what will happen, it will actually turn purple to colorless after a reaction. So this is another item for you to think about it. And of course, for testing a reducing agent, we can also add the solution form rather than using the paper. And naturally, if there is actually, when the potassium manganese actually gets reduced, what will happen is it will actually turn from purple to colorless. So generally, this is the explanation of using potassium manganate. Basically, what will happen is the MnO4 minus will be reduced to your Mn2 plus ions, and this change in oxidation state decreases from a +7 to +2. How is it a +7, right? So let's do a calculation. So let's say we let X be the oxidation state of Mn, and 4 oxygen molecules, so atoms, so it's -2, you get -1 charge. So we could see that X minus 8 equals to -1. When you bring over, it'll be 8 minus 1 equals to +7, which is this Mn over here. Okay, and then of course Mn2 plus is just 2 plus 2 lah. Then so this is the one whole reaction kind of thing. Okay, so generally that comes to the end of our this particular chapter. And if you need time, do watch the video back, and then all the best. Thank you.